get Zoom set up. Sorry about that. I should have had this on already so you could be helping me watch. Okay, so let me do my moving around. You can't see it, but I'm having to adjust the thing. Let me just get Jordan moved over. Okay. All right. Now, can you find where this slide is in the book? As you gain experience using integration by parts. Okay, there it is. I think I found it. Yes, there it is. Okay, so we need to go up one slide. Okay, there we got it. I finally found it. Sorry about that. Now, any questions, issues, problems, concerns before we get going today? Sure. A question about what? Okay. That was the chapter 7 test? Okay, yeah. You can ask it right now if you want to. Okay. Okay, well, let me, while we're here, okay, this is, let me make sure I get in the right place. It's the, yeah. All right. And we're talking about the chapter 7 test, not the chapter 5 test, right? Okay. So let me thumb through here and find it. Okay. And how does that question 5 start? Oh, 4. Find the volume of a solid generated by revolving the region. Is that the one? Y is equal to x squared. Y is equal to 20x minus x squared. Okay. Now, that's the one you're interested in. Okay, let me... Okay, that's what I'm trying to find. I wanted to make sure I copied it right. I'm reading off the, and I can't believe all these pages. I can't land on, okay, here we go. I think this is number 4. Is that right? Okay, now see, I have many copies of the test. I want to make sure I'm doing the right one. Is find the volume of the solid generated by revolving the region bounded by the graphs of, and how does yours read then? Okay, are you sure that's not y is equal to 9x squared? Okay, good. Okay, see, I wanted to make sure I was looking at the same problem you were. So let me just make sure. This is number 4. Oh, I know what's going on here. There it is. Okay. Now, what specifically is your question? Okay. Yeah, good question. Okay, now I see what I think I understand what you're asking now. Okay, so what I'm going to do, I don't know where to set all this stuff and not lose it. Okay. Oh, wait. Here's 2 more people coming in. This will give us perfect attendance today, but I got carried away with the problem and forgot what I did with my grade book here. Okay, Ashton's here and Andy's here. The 2 A's are here now. Good deal. Now, that's not necessarily grades A's, but whatever. All right. Perfect attendance. Way to go, folks. Glad you're here. I see y'all haven't quite gotten in yet, but hopefully you can hear me anyway, but if not, we'll do it. Okay, the question was on chapter 7 test, example or test question number 4. Find the volume of the solid generated by revolving the region bounded by the graphs of what? Yeah. What, the chapter 7 test? Okay, let's pause a moment there then and go back and find it. So I'm going to Blackboard. And I'm in the wrong class right now, so hang on. Okay. And Math 126, there it is. Okay, you see where we are in Blackboard. I just clicked on the class. Okay, now I have to go and check. I'm going to have to move y'all a little bit here because Blackboard is awkward to navigate. So I'm going to look first under weekly assignments. Okay, and does anyone remember what week I put this out there? Was it week 10, 9, or 10? Okay, let's try 9 first. Yep, there it is. Okay, do you see where I went to week 9 under weekly assignments? Okay, you see chapter 7 test. Let's see what's there. I'm going to click on that and see if it's indeed here. Sometimes I can place it here and sometimes I can't. Yeah, there it is. Math 126 test 2. You can come over here to the 3 dots here that for some reason they call an elliptical, which makes no sense. And if you click on that, you'll see it says download original file. If you click on that, then you'll see it come down to the lower left corner and start downloading, and then when it finishes downloading you can get it there. Okay, so that's one place you could get it. Okay, but I'm going to show you another place as well. I hope I put it there. I try to put it in a couple places. Now I'm going to have to move y'all again. Okay, and I'm going to come back up to the top and you see Blackboard messages here, the envelope. I'm back on the home page, the content page. You see where I am? Okay, if you click on that envelope that says messages, click there, and then you'll see attached is the chapter 7 test. So here was the chapter 5 test, there was the chapter 7 test. Now, I have had a few students in the past that either have a different version of Word on your computer than what you have on I have on mine. If you cannot see all of the equation mode stuff that's on that, let me know, and I'll also load a PDF of this, because sometimes Word doesn't transmit well. I really dislike Microsoft products because they will upgrade a product and make it so the previous product won't read it anymore, making you buy the new product, and I find it just totally irritating. So anyway, that's 2 places, but they're both in Word documents. If you can't get it to read properly, then let me know and I'll put it out there as a PDF form as well. Okay? Alright, now let's since we're here anyway, go here. Okay, 126, and this is test 2. There's the Word document right there. I hope this is the one. That's why I'm banking on it being the one. Okay, does that look like your, oh wait, you can't see it, can you? Okay, so let me do this. Okay, Now I got to move y'all out of the way again. Sorry about this. This Blackboard is such an awkward package. Okay, is that the problem you were asking about? Number 4 right there. Okay, good. Okay, now I'm going to try to see if I can write on this. If not, I'll manage something else. Okay, and this is just going to be a rough and dirty. Okay, I'm going to go probably all over the screen here if it'll write. Let me see if it will. Let me draw my graph here if it'll draw. No, it will not draw. Sorry about that. So let me now get out of that and go to the whiteboard. I thought it would let me draw on that, but it won't. Okay, now I've got to move y'all again. Sorry. Okay, I've got to move this taskbar, which is of course in the way, and I've got to move my whiteboard so I'll have the maximum amount of white space with which to work. Okay, I think that's got it. Okay, now we'll try it again. Let's do my axes. Pretty ugly vertical line. Okay. All right. This is going to take some doing here. Okay. Now, here's the graph we're dealing with. Y is equal to 9x squared. But notice here at the end it says going up to the line y is equal to 36. Okay, that's the big pain in the neck right there. Sorry about that. Okay, so what I'm going to do, there's my origin right there. And let's just tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, now y is equal to 9x squared. Okay, let's see, y is equal to 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. I'm just trying to figure out the best way to draw this. Okay. I'm just going to try something now. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and 55. Okay, that just gives me some scales to work with. All right, now my x-axis is not going to be nearly scaled like that. Okay, here's what I'm going to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll go a minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, something like that. Okay, so let's pick our points here. Now remember, okay, let me see. Where in the world is my pen? There it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6. I'm going to make this 1 here. This is really an exaggeration. 1, 2, 3, 4, 5, 6. Okay, there's 2. Now this is really spread out. My x-axis is way spread out. My y-axis is really compressed. So this is going to be a bit weird looking, but I hope it'll show you what you need to have. Okay. So y is equal to 9x squared. Okay. Well, obviously when x equals 0, y is equal to 0. Okay. And that aggravates the fool out of me. I can't get it to draw. There we go. 0, 0. There's a point. Okay. Now let's do x equal 1, which is way over here, and that would be 9. Okay. So that would be somewhere up here, right about there. Okay. When x equal 2, that would be 4. 2 squared is 4 times 9 is 36. Okay. 36 is somewhere right up about there. Okay. So there's the thing. So here's what our parabola is looking like. It's really, really flat here going up to there. Something like that. Okay. Mine's not drawn too well. Y is equal to 0. Well, that's y is equal to 0 is a x-axis here. So we got that one. X equal 2. Here's x equal 2 right here. Sorta. Okay. Okay. Y is equal to 0. Okay. So this is the region we're talking about right in here. Do you see where I'm talking about? That's the region between this graph, this parabola here, okay, y is equal to 0, which is the x-axis, and x equal 2, which is this vertical line right here. Okay, and we're revolving this around this line right here, which is y is equal to 36, just above there. So this thing is going to go around that line here. Okay, that's pretty ugly, but I hope you sort of see what we're doing. Okay, now does that give you an idea where to go from? Is that going to answer your question, or do you need a little more suggestion here? Okay, that was exactly what I was going to say. It looks like to me this would be a reasonable thing to do your dx's here. Okay, and if you're doing a dx, and you remember this is revolving around here, so this is going to be a washer. Okay, right? Okay, because up here will be the, get out of there, the other part of that, and I don't know if I can draw this reasonably, but I'm going to try to do like that. Now I didn't leave myself enough room, so you see we've got the washer that goes here, so I can't do, there's that part of the, and that goes on up, and this part here. So yeah, there's your washer, and mine's not drawn too well. So yes, I would do 0 to 2 for your dx's here. Now the thing to watch out for are your radii. Okay, now you know what the radius is here from this place to that place. As you revolve that around, that's just going to be 36. That's the outer radius. The inner radius is going to be 36 minus, and I didn't write it down, let's see, y is equal to 9x squared. Okay, so that's going to be this, the inner radius. Okay, so the outer radius is just going to be 36 because you're going from here to there, and that's going to be 36. The inner radius is going to be from 36 to this place down here, which is 9x squared. So it's 36 minus 9x squared. Okay, does that give you what you need? All right, good question. It's a rather bizarre problem. I'm sorry, that was in the test bank, and I just was typing it in as I did, and I didn't realize it was such a sort of bizarre, but I mean, it's reasonable. It's just you have to scale it crazy to get it to see what's happening. Okay, all right, good deal. All right, Shirley, Any other questions? Great question, by the way. It's exactly the kind of thing I want you to make sure you understand before you spend too much effort and time and energy doing something that you're really not understanding what you're doing. So I'm glad you asked. Any others? All right. If not, let me go back to the PowerPoint. Okay. And I can't tell which is which. That's it, I think, right there. Okay. Now, that was the end of example 1. And we still have to do, and we've done example 2, example 3, example 4, and example 5. We're just getting ready to do example 6. Okay. Now, and this is on page 527, section 8.2, chapter 8, integration techniques and improper integrals. 8.2 is integration by parts, and example 6 is finding a centroid. Now, sort of a pain in the neck here is that I think they sort of took the centroids out of the requirements here, but then they put it back in to give you an example of it. So I will try to give you a quick and dirty on this, but don't sweat this too much. I'll try to show you how you work these, even though I think the state took out the centroids as part of the requirement for the course, but I'll let you do. A machine part is modeled from a region bounded by the graph of y is equal to sine x. So let me sort of do, whoa, goodness gracious. That just drew there without me even touching the page. So let me see if I can clear that. Okay, so I'm going to try again to draw a vertical axis and a horizontal axis. Not very horizontal, but you get the general idea. Okay, now machine part is modeled by the region bounded by the graph of y is equal to sine x, the x-axis, and x going from 0 to pi halves. Okay, so it said find the centroid of the region. Okay, so let me do, that'll be 0. Let's come out here and say this is going to be pi halves, just to pick a place. This up here is going to be 1. Okay, and we know the sine graph basically is heading up this way and flattens out right around x equal pi halves, y is equal to 1. So that's your pretty ugly looking sine wave. Okay, this is y is equal to sine x. Okay, now the x-axis, of course, is y is equal to 0. Why they say it one time in one way and another, and the region from 0 less than x is less than pi halves. So we're talking about this region here. This is the machine part right here. Okay, and we want the centroid of that. Now we haven't talked about what the centroid is, so let's get just a little bit of background on that. Okay, now the first thing they're going to do is find the area of this region. Okay, and that's merely going to be, do your dx's here. Okay, dx is going to be going from 0 to pi halves, and you're going to sum all these up. The height of that rectangle there is sine x, going from 0 to that. So the area of this region right here, we'll just call it area, is equal to, this is pretty simple, the integral from 0 to pi halves of sine x dx. Okay, height of that is sine x minus 0, width is dx, the area is just a sum of all those. Okay, well, what's the antiderivative of sine x? minus cosine x, evaluated from 0 to pi halves. Okay, well, when cosine is pi halves, now remember cosine starts here at 1 and it goes down to 0 at pi halves. Okay, so that would be a minus 0, okay, which I'm just going to leave off. Minus a minus, which is plus cosine of 0. Well, cosine of 0 is 1. So that's just going to be 1, okay? That is the area of that region, okay? And you may say, why are we dealing with an area, okay? Now, the coordinates of the centroid, you evaluate the integral for what they call y bar, okay? And what y bar is, and this is being given to you here, y bar is equal to, we're going to have to come back and do x bar as well, but y bar is equal to 1 over the area, which we just have calculated. That's going to be 1 over 1 if I can find my pen here. So that's just going to be 1 over the area, but the area is 1, so that's going to be nothing, okay? And then we're going to do the integral from 0 to pi halves again, okay? Now what we're going to be doing here is finding the centroid, which is the midpoint here. Now here's what an assumption is. This plate, whatever this thing is uniform thickness, uniform density. We're not having any kind of a variable density here. So what we're doing is doing that. Well, this is exactly 1/2 sine x. So that's, if I can get the pen to show it, there it is. So I'm going to put the 2 here, and that would be sine x here. 1/2 sine x, okay, dx. Okay, now this seems like a pretty okay, I put my dx in there too soon, sorry. I'm trying to find, there it is. This pen is pretty hard to follow sometime. Okay, so there's your 1/2, okay. Now, that's 1/2 sine x, that's how far you go, okay, times the height of this. So it's half the height times the height, okay. Now that's, it seems a bit bizarre, but that's exactly what it is. And so basically this gives you sine squared x. Now actually, since we didn't do centroids, they took it out. Let's just skip this problem because this is just too many assumptions here and you don't have the background for this. So I could carry it through just like they do in the book, but we don't have it. Let's do this instead. Rather than worry with centroid, let's just do the calculation the way they want us to do it, okay? So I'm going to forget about the centroid part of it, but just let's, okay? What we're going to do is just pretend that they say, here is the function we want you to calculate, okay? Let's call it y, we won't even call it y bar, is equal to, and we won't mess with 1 over a, that's just a 1. We're going to do this integral, 0 to pi halves, okay, and we'll do a 1/2 here, okay, sine squared x dx. Okay, now that in itself is a big enough pain in the neck to deal with, okay, and that's all we're messing with now is that, okay. Now here's how we do an integral such as that. we start with the fact that sine squared x, sine squared x, there is a trig identity here, okay? And I don't know if you remember this trig identity, but here's what it is, okay? I'm going to write it down kind of in gory detail for you. Okay, number one, we know that sine squared x, if I could get the pen to show up. I swear this pen gets lost. There it is, okay. We know that sine squared x is 1 minus cosine squared x, right? Okay, now, that's what sine squared x is. Okay, but it's a, I'm trying to think, double angle or a half angle formula, okay? They don't even name it here. Here is an identity for you, and I'll tell you where to go to look for it. If you go to the front inside cover of your text, okay, remember that cardstock page in the beginning. The front side of that is derivatives and integrals. Flip over to the back side of it and it's your trigonometry. And this is the function we're looking for here. Well, I thought I would see it here. There, it's not in great form, but it is in good form. Okay. I wrote this one here, but I think I will go on and change it on you. Whoops, I'm on the wrong pad. Okay, let me erase this one. I'll go straight to the one you need. I was going to derive it for you, but that's just going to take too long. So let's just go here to the book. Okay. Now, it's a double angle formula for cosine. Cosine of 2x. Now, there's three different ways you can write cosine of 2x. One way is cosine squared x minus sine squared x. We don't want that one, okay? The second one is 2 cosine squared x minus 1. We don't want that one. We want the third one. The third one is cosine 2x is equal to 1 minus, and if you're in the book there, 1 minus 2 sine squared x. Now here's why we want that one, because here we have sine squared. So we want to solve for this sine squared here, okay? You see, we can't really integrate when we've got the square here. We need this to the first power. So this is going to reduce your power from squares to first power. Going to change your function, but that's okay. Okay? So let's solve this for sine squared. So what I'm going to do is add 2 sine squared x to both sides. I'm sorry. Okay? I'm also going to subtract cosine 2x from both sides. Okay, I'm running out of room there. So these go away, and we get 2 times the sine squared of x is equal to 1. This goes away, and we have minus cosine 2x. And we're almost there. Divide both sides by 2. Okay. So now we have another representation of sine squared x. 1 minus cosine 2x divided by 2. So let's pull out that second 1/2. We already had this one here. Let's pull out this one. Okay. So that's going to be 1/4 the integral from 0 to pi halves Okay, and your sine squared x is going to be 1 minus cosine of 2x, and we've already taken out the 1/2 dx. Okay, now, frankly, I mean, I know what they're doing, but I'm wondering why in the world this is here under integration by parts, because we really don't need integration by parts to do this, that I can see. Okay? Yet. We will need it in a minute. Okay? So, let's do this integral here. This is going to be 1/4, and the antiderivative of 1 is x. So this will be x minus, and the antiderivative of a minus cosine 2x is going to be a sine 2x over 2. Okay, we're going to evaluate that from 0 to pi halves. Okay, so this gives us, when you plug this in, that gives you a 1/4. Okay, pi halves minus, okay, sine of 2 times pi halves, that would be pi. Sine of pi is 0. Okay, then we'll do a minus 0 and another 0 here, so that's all you got. Okay, so this is going to be pi eighths. Okay, so that's this integral here. No integration by parts needed. That was just doing the integral. Okay, and that's what they got here. Now, and that, the reason we were doing that was giving you what they said, the y bar. And we're not going into what the centroid is, but that was the part that gave you the y. Now the part that gave you the x, this is the part that you need integration by parts in. Okay? And you don't need to know why this is, but this is this. So you can evaluate the integral, and it's the x bar. I'm just going to call it x here. And that would be 1 over a, and that's just 1. Remember, that was left over there. And then this will be the integral from 0 to pi halves again. Now this time, it's your distance from the y-axis times that centroid that we were talking about. So this is going to be x times sine x. Okay? Okay, dx. Now, without having to know what the centroid is, this is the integral that you would have been solving for. Okay? Now this looks rather bizarre. I really should put the bar over there because this x is not the same as that x. Okay? The y was no problem, but the x is, that looks confusing. Okay? This does require integration by parts. Okay? Now, I know it was last week, long time ago. How does integration by parts go? Okay, just as a reminder, this is a product. One of these is going to be a u, the other a dv. What we want to choose is the u, the thing that when we take a derivative of it, it gets simpler. What we want is the dv, is when we integrate it, it doesn't get any worse. Okay, so the u here is going to have to be the x part, and the dv is going to be the other part, sine x dx. And remember, the d's always go together. Okay, then du is equal to dx. That's pretty easy. That got a lot simpler. When you integrate both of these, okay, this gives you v is equal to, and the antiderivative of sine x, just like we did a little bit earlier, is going to be minus cosine x. Okay, and this is, we're not going to evaluate anything yet, but that's going to be minus cosine x. Okay, now where do we go from here? This integral here is going to be the product of u times v, which is minus x cosine x, and it normally would have been a minus, but then you've got a minus here, so that's going to be a plus the integral from the bottom line here. That would be cosine x dx. Okay, now this you're evaluating from 0 to pi halves, and this you're evaluating from 0 to pi halves. Remember, when you do have a definite integral, you do, this is so aggravating. Okay, you do evaluate this there too. So this will be a minus pi halves times cosine of pi halves. Well, cosine of pi halves is 0. Minus a minus, okay, that'll be a plus pi half, I'm sorry, 0 times cosine of 0 is, well, guess what? That's going to be 0, because when you plug a 0 in. So you get nothing from this part. What do we have here? This is the antiderivative of cosine x is sine x, and that's evaluated from 0 to pi halves. Sine of pi halves is 1, and sine of 0 is 0. So you just get 1. Okay, all that for that. Okay, so the centroid would have been, your x bar is 1 and your y bar is pi eighths. You don't have to worry with that. Okay, but they do show you that in the book. But what I thought was worthwhile was at least doing the integral, showing how you do the integration by parts. This one did not require integration by parts. This one did. Okay, so that was example 6. Normally we would have done centroids earlier and would have made sense to carry that through. Here we're not doing that. Okay, so at this point, sorry about that, let's move on to, this is example 1 that we finished a long time ago. Now we're here. This is top of page 528. I finally found where it was. As you gain experience in using integration by parts, your skill in determining which is the u and which is the dv will increase. I think you're already well along the way there. The next summary lists several common integrals with suggestions for the choice of u and dv. So here's that thing, and this is, like I said, top part of page 528. This is your summary. I don't think I need this anymore. I'm going to apologize ahead of time. I did have my treatments last week, Thursday and Friday. They went really, really well, but I am basically exhausted now because my red cell counts were already very low. I was very anemic, and the treatment usually drives them down a little further. Now, it wiped out the white cells, I'm pretty sure. We haven't done a test, but I could just tell there was a battle going on in there, and they were getting beaten up by the chemical, by the monoclonal antibody. So that went really, really well. Had no, the first day, that 10% thing, there were so many white cells in there. I was hot. I could just tell the battle was going on in there. The second day, when I had the 90% dosage, it was just a piece of cake. I mean, the 10% had wiped out, I think, most of the drugs, the malignant cells. Okay, a good number of them anyway. So now, as the time has gone on, the drug also attacks a few of the red cells. So where I was anemic before, pretty anemic, now I'm even more so. So I'm just dragging. So I apologize for this. Every now and then I'm going to have to drink a soda, do something. I'm just running out of energy pretty quickly, but it's going to get better. Okay, so this is the typical pattern of it. So pause for just a moment here and let me try to boost a little bit of energy there. All right, so here are your summary for the integration by parts. Some of the common integrals that use integration by parts. For integrals of this form, which we just had x to the first power times, I believe it was sine, okay? Perfect, okay? Your u will be the power function because you take a du and it gets simpler. It reduces the power every time. The e to the ax isn't going to get any worse because you integrate e to the ax, you get e to the ax. Well, you may have a denominator of an a in there, but that's okay. That gets better. Same thing here. Integrate the power function, it gets simpler. Differentiate the power function, it gets simpler. Integrate the sine, and it doesn't change. I mean, it becomes a cosine, and you have a 1 over a, but you can live with that. Those are, pretty easy things. They don't get any worse. This one, you differentiate the power function. Again, it gets simpler. Integrate the cosine, it goes to sine over a, but that's okay. So your u will be your power function. Your dv will be either e to the ax, sine of ax, or cosine of ax. Okay. Now, that works well when you have that. But you can't always say the power function is going to be your u. Because if you have a log function here, you can't make that your dv because that's not going to work well. You can't integrate a log x. So here, this is going to be your u, and this is going to be your dv. Okay, sure, this is going to get worse, but the thing is, the derivative of log x is 1 over x, so that's going to wipe out one of the ones you just picked up. So that works okay. This arc sine, okay, same type deal there, because I usually just look these up because those are such pains in the neck to do. So the arc sine and arc tangent, they usually just let those be just like the log, let those be your u, and then go the other way on that one. Usually we won't run into these that often, but when you do, just remember it's just like the log. Okay, now how about this one? E to the ax and sine bx, or e to the ax and cosine bx. Guess what? It doesn't matter which one you do, because both of these, when you integrate, they don't, or differentiate, they don't get any worse. When you integrate, they don't get any worse. So you can use whichever way you want to do. They suggest this way. That's fine, perfectly fine. It really doesn't matter because both of these don't get any worse when you differentiate or integrate. Both of them. So you can do whichever. The only thing you have to watch out for those is if you have to do multiple ones of them, make sure you keep in the same pattern. Don't use this as your u first and then go back and make it the dv, because then you're undoing what you just did. So that's the only thing to watch out for that one. So let's move on to, yes, in problems involving repeated applications of integration, okay, they didn't give us any examples with the other. Repeated application of integration by parts, you can use this tabular method, which we're going to illustrate in example 7. This will be the last example in this section, to help you organize your work. And this method works well for integrals of this form: x to the n sine x, x to the n cosine x, or x to the n e to the ax. Okay, now remember that's this number 1 here. Okay, that works really well on these. Not so well on these, though it will work. You just have to be careful with it. And not so well, well, it works okay on these too, but it works really, really well on this first one here. So let's do example 7. Now, going to try to do it. And this is also example 7. You can find at larsoncalculus.com an interactive version of this type of exercise. So that's what we're going to do. and here's how we begin. Okay, it seems a little cookbookish, and it really is, but it works well. The first thing you do is alternate your signs. Okay, that's it. You just put plus, minus, plus, minus, plus, minus. I'm not going to need that many, but I'm just going to write them out there in case you had a really big thing. Okay, now what you do then is your u, and your u here would be x squared. Remember, you want that to be, so here is going to be the u, and the u is going to be x squared. Okay, and the dv, they put v prime, which is okay, and that's going to be sine of 4x. Okay, now what you do here is take derivatives of this. Okay, the next one's going to be 2x, and the next one's going to be 2, and the next one's going to be 0. You stop there. We don't need to go any further. Okay, you're integrating this. The antiderivative of sine of 4x is going to be 1/4 cosine of 4x. Okay, except that's going to be a minus. Not having to do with this minus over here. These are just alternating signs. This is going to be minus because the antiderivative of sine is minus cosine. Antiderivative of this would be another one, 1/16, and this would be then a sine of 4x. Okay, see, that didn't change because the antiderivative of cosine is positive sign, but that minus sign carries with it. Okay, this one would then be one more time, and this is going to change to antiderivative of sine is minus cosine, so this will be 1/64 cosine 4x. Okay, now that's the setup. Okay, first thing you have is alternating signs. The second thing is your u's here that you differentiate each time, and then your dv's that you integrate each time. Okay, now we don't need all those, but I'm just showing them to you. And here's what you go. You start with the plus sign here, you go here, and then you don't go across, you drop down one. Okay, so what we've got here is, remember, this is going to be your v, u times v. Well, it's a positive u times v, but the v is a minus, so that's going to be a minus x squared over 4 cosine 4x. Okay, then we're going to have a minus this times that. Well, a minus times a minus is going to be a plus, and then we're going to have a 2x over 16, so that would be x over 8, and that would be then the sine of 4x. Okay, that gets you across like this. Then the next one's going to be a plus 2 times 1/64, so that would be 1/32 cosine of 4x. You do the plus times the 2 times this one, and then the next one's a 0. You stop. So without doing an integration by parts or anything else, you just let the table do the work for you. This thing right here would be minus x squared over 4 cosine 4x plus x over 8 sine 4x plus 1/32 cosine 4x. Okay, plus c. You have to have your plus c in there. Okay, and that's what you got without having to fiddle with integration by parts. Let your table do the working for you. That would be minus 1/4 x squared cosine 4x plus 1/8 x sine of 4x plus 1 over 32 cosine 4x plus c. So basically, how you do one like this is just first alternate signs, because you know the first is going to be plus, minus, plus, minus, plus, minus. So do that. Find the one that you're going to have as your u and carry that all the way through. So u is going to start as x squared, derivative of that is 2x, derivative of that is 2, then you get to a 0, you're going to stop at that point. Your dv is the other side of it, and then you integrate that, and you write down this one, though you really don't use it anywhere, but write it down. Then the antiderivative of sine of 4x is going to be minus 1 over 4 cosine 4x, because derivative of the antiderivative of sine is minus cosine, and then the antiderivative of 4x is going to be 1 over 4. And then you do this again. Antiderivative of cosine would be sine, but you already had your minus on there. You bring down another 4 here, so that's where that comes from. Antiderivative of sine is going to be minus cosine, so that changes that minus to a plus and divides by another 4. So you just do your integration there. Sure, the fractions are a little more complicated, but they're just numbers, that's all. Your function is just going back and forth between sine, cosine, sine, and cosine. Alternating signs, kind of, plus, minus, minus, plus, plus, minus, minus, plus, yeah. You'll get used to that. But, and then you just remember, you go across the first one, straight across, then down 1. Straight across, down 1. Straight across, down 1. And until you hit that 0, stop. Okay. That's how we use the tabular method. All right. Any questions on that? I thought it's a little rushed on that, but they did it, and it's fine. Homework exercises here. I always suggest that you take a look at your concept check, okay, to make sure you understand what's going on there. The first 4 are concept checks. If they're in the back of the book, probably just the 2 odd ones would be back there. But the homework exercises, any of the odds 5 through 9, they're both at Calc Chat, 5's at Calc View. Either 11 or 13, both at Calc Chat, 11's at Calc View. Any of the odds 15 to 33, they're all at Calc Chat, 15's at Calc View. Either 35 or 37, both at Calc Chat, 39's at Calc Chat, 41's at Calc Chat. Any of the odds 43 to 51, they're all at Calc Chat, 45's at Calc View. Any of the odds 53 to 57, they're all at Calc Chat, 55's at Calc View. Either 59 or 61, they're both at Calc Chat. 63 or 65, both at Calc Chat. 67, Calc Chat. 69, Calc Chat. Any of the odds 71 to 75, Calc Chat. 77 to 81, Calc Chat. 83 to 85, Calc Chat. And then any of the odds 87 through, and you don't have to worry with the centroids unless you just want to go through those, but 87 through 91. Then 93 should be at Calc, and all those are at Calc Chat. 93's at Calc Chat, 95's at Calc Chat, and either 7 or 99 should be at Calc Chat. Any questions on integration by parts? Okay, let's watch how they did this one. I'm sorry, I forgot. This is one that they do. They may do a better job of describing than me, so let me get this erased. So, solution, begin as usual by letting u equal x squared and the dv equal sine 4x dx. So put the x squared here, the sine 4x. They don't put the dx here, but you can put it there if you'd like to. Okay? Now, create the table consisting of 3 columns. The first column is strictly going to be alternating signs. Plus, minus, plus, minus, plus, minus, plus. Okay. The next is going to be your u that you chose here. U is equal to x squared. Then start taking its derivatives. 2x to 0. Once you get a 0, stop. Okay. The dv, which is your sine of 4x, when you take the antiderivative of that, you get a minus 1/4 of cosine 4x, take the antiderivative of that, a minus 1/16 of sine 4x, antiderivative of that, a minus 1/64, because every time you're dividing by the 4, the antiderivative of sine is a minus cosine, antiderivative of cosine is a positive sine, antiderivative of sine is negative cosine. So that gives you a rather bizarre but standard pattern here: plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus. Yeah, as long as you did that, that would be fine. Okay, you won't need that many, because when you get to here, you'll stop. Okay, and then you just follow your arrows straight across for this one: positive x squared times a minus 1/4 cosine 4x, minus 2x times a minus this, so that make it plus 1/8 x sine 4x, and then a plus 2 over 64, which is 1 over 32 cosine 4x, and you stop here when you get to the 0. Okay, the solution is obtained by adding the sign products of the diagonal entries. Go across from the plus minus sign to the function, the u function, and then go down that diagonal entry to the dv. Okay, so that would be, that one would give you the minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus your constant c, if this was a indefinite integral or improper indefinite integral. Okay, and that was the end of the slideshow. Sorry, I should have done that before I made the assignments, but you got it. All right, so let's end now I've got to get to 8.3, and I don't know why it does it. I had it up here, it was there, and now it's not there, so I have to do that. And then let's try another screen share again. It's just sort of a okay, it's still not showing, so let me, you have to hold your mouth just right to get this to work. Okay, let's see if it's going to show here now. There it is, 8.3. Okay, got it. Now 8.3 is, let me go from current slide. Chapter 8 is still integration techniques and improper integrals. We're going to focus on integration techniques though, chapter 8. 8.3 is now talk about trigonometric integrals. And actually we already had one of these when we did that centroid. Okay, that was a trigonometric integral. I thought they sort of jumped the gun on you there, but it's okay. It just got you ahead. I need to move this taskbar, which you probably can't see, out of the way. So let me get this down here at the bottom, out of the way. And let's proceed 8.3. Well, I'm going to try to proceed. And let me see if I need to move y'all over a little bit to the right. Yeah, okay. So let's see if I can proceed. Yeah, here are our objectives for 8.3. Solve trigonometric integrals involving powers of sine and cosine. Last time, remember, we had a sine squared. We showed a technique for doing that. Solve trigonometric integrals involving powers of secant and tangent. We'll get to that one. And we'll solve trigonometric integrals involving sine cosine products, not just powers, but products. Okay? So, here's where we begin. Okay. Integrals involving powers of sines and cosines. Okay. In this section, you'll study techniques for evaluating integrals of this form. The integral of sine m to the mth x times cosine to the nth x and secant to the nth x and times tangent to the nth x, with all those being dx's, where m and n are positive integers. We don't have them being fractions. We don't have them being decimals. Sorry. We don't have them being negative. They need to be positive integers. Okay? To find the antiderivatives of these forms, we try to break them into combinations of trigonometric integrals to which you can apply the power rule. That's sort of the secret here. Okay? So, how do we proceed? For instance, you can find the integral of sine to the fifth x times cosine x dx with the power rule. Okay? Basically, it's just a simple u substitution. Let u equal sine x. What's du then? Cosine x dx. Well, then this will be u to the fifth times du. That's it. It's nothing new, really. Okay? And that is exactly what you would get here. And that would be u to the sixth over 6, because u to the fifth, u to the 6 over 6 plus c, sine to the 6 over 6 plus c. That's it. Okay? Now that's easy. Okay? They'll get a little more complicated, but that's basically your fundamental approach to this. Now, what if, though, it wasn't just cosine to the first power, it was cosine to the nth power? Okay? Well, here what you do, you need to apply the power rule, but you have to use some additional relationships. And here they are, your favorites of all time, the Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. And then the one we used in the last section, sine squared x is equal to 1 minus cosine 2x over 2. Now what did this do for you? This reduced a sine squared to a cosine to the first power. It's way easier to integrate something to the first power than it is a square. So this was basically a power reducing formula for sine squared. Same thing here, cosine squared is 1 plus cosine 2x over 2. The power reducing formula from x squared to x to the first power here. I mean, cosine squared to cosine to the first power here. Those three we're going to use a lot. This one we're going to rearrange and either have sine squared as 1 minus cosine squared or cosine squared as 1 minus sine squared. We'll use that, then we'll also use these two to reduce the power to something easier to integrate. That's the technique. So let's see how we're going to do it. Now, don't try to memorize these guidelines, but just get the concept of the guidelines in place, and I think you'll see what's going to happen with those. So the guidelines for evaluating integrals involving powers of sine and cosine. When the power of the sine is odd and positive, okay, remember we always have them being positive and have them being integers. So odd and positive. Save one of those signs, okay, that sine factor, and convert the remaining ones to cosine. Because you see, if the power for sine is odd but positive, so the fifth power, okay, pull out one sine. That leaves you sine to the fourth power. Well, sine to the fourth power, we can use your Pythagorean identity to simplify. Okay? So, if this is an odd number, 2k plus 1, k is any integer here, that's the odd number. It doesn't matter what the cosine power is. It really doesn't matter at all. Okay? But make sure the sign is odd. If it is, factor out one of those signs. Okay? That's going to become your du. Okay? And then the rest of the signs, they're got to be even now. You factored one odd one out. That's going to be even. So that's going to be sine squared raised to the kth power, because this is 2k here, right? So you can take this sine squared and make that into 1 minus cosine squared, our Pythagorean identity. And then you have some power of cosine squared times another cosine. Well, guess what? It doesn't really matter. All these are cosines. The derivative of cosine is minus sine. So that's what we use. And that will be our technique. Now, what about if the power of cosine is odd and positive? Then you just do the reverse. Pull out one cosine. That's going to be your du. And then the rest of your cosines are going to be even. Break that into cosine squared raised to however many even powers that is. Make this one minus sine squared. Multiply that by here. And now you got everything in terms of sines. And this will be in terms of sine. That will be in terms of sine. Derivative of sine is cosine. So that's going to be your U substitution. Now, here's the problem. What if they're both even? If either one of them's odd, easy to do. If they're both even though, and non-negative, of course they have to be non-negative, here's what you do. Make repeated use of the formulas sine squared because it's going to be even. Remember that one we had here? This one, these two here? Make that 1 minus cosine 2x. That's your power reducing formula. Or cosine squared power reducing formula. So what you do then, make repeated use of those formulas, breaking them down from an even power to one less, an even power to one less, and keep doing that until you get down. And when you finally get it to an odd power of cosine, which only take one time, then you go back up here and do that. Because now you have an odd cosine. These are always going to be cosine, never sines. So you go back to this one. Now that's a lot of blah, blah, blah. Okay? When you're actually doing them, hopefully you'll see it makes more sense. So let's do this one. Okay. Now, what we're trying to do is integrate, if I can get my pen to show up, there it is. Sine cubed x cosine fourth x dx. Okay. Now, first thing you look for are either one of these odds. Yes, the 3 is odd. So let's break out one sine. This will be the sine of the integral of sine squared x. You pulled out one of those. Cosine fourth x. Doesn't matter what really that is. Okay. And then that one you pulled out of here, let's put that as a sine x dx. Okay. Now, sine x, excuse me, I'm just almost losing consciousness here. Hold on just a minute. Let me boost the energy a little bit here. This sine x is the derivative of cosine. So we want all these to become cosines. And that's fairly simple to do. This will be the integral of, well, sine squared is 1 minus cosine squared x, right? That's from your Pythagorean identity here. Where is it? Oh, well, there it is. Okay. Sine squared x is 1 minus cosine squared x. So you get everything except that one little sine, everything else in terms of cosine. Okay. This one's already in terms of cosine. So we'll just write that as cosine fourth x. Okay. And then this will be your sine x dx. We're going to see what's going to happen with that in just a minute. Okay. My phone's making noise, and it's some number I don't recognize, so it can make all the noise it wants to. Okay, let's multiply through. Cosine fourth x times 1 is cosine fourth x minus cosine squared times cosine fourth is cosine 6x. Okay? And you got this times sine x dx. Okay. Now, here comes your good old u substitution. Let, okay, what's the innermost part of your most complicated part of this problem? Cosine. So let u equal cosine x. Then du is equal to, what's the root of cosine? Minus sine x dx, right? If u is cosine x, du would be minus sine x dx. Okay? Now, let's see what we've got. We've got the integral of cosine to the fourth. Well, that would be u to the fourth, because u was cosine. Minus cosine to the sixth. Cosine is u. That's u to the sixth. Okay? Now, the problem is we've got a minus sign here. So let's do it this way, I guess. It doesn't really matter. Divide everything by a minus 1. Or multiply it by minus 1. It doesn't matter. Okay? These go away. And then what you would have would be a minus du. Because the sine x dx is going to be minus du. Okay? So I'll put the minus out here. Now, indefinite integral, all you do is minus u to the fifth, just a good old power rule, u to the fifth over 5, minus a minus, which is plus u to the seventh over 7 plus c. That's it. I mean, you're done, almost. Except you go back and plug in what u is. U is cosine. So I'm going to write it this way. 1/7 cosine to the 7th x minus 1/5 cosine to the 5th x. Just plugging in u is equal cosine x everywhere you see it, plus c. That should be it. So let's see what they got. They started off with minus 1/5 cosine 5th x, why I don't know, plus 1/7 cosine 7th x plus c. Same answer, they just wrote it in a different order. Okay. Any questions on that? Okay. Now, they have a little blurb here on technology. A computer algebra system used to find the integral gives you a different answer. And basically all you have to do is rearrange things. That's a much more complicated answer than the one we got. I like the one we got. All right. Any questions on this before I erase? Okay. Let's see how they did it. Okay. Because you expect to use the power rule with u is equal to cosine x, why did we expect that? Because the derivative of cosine is sine, and you have an odd number of sines. So that's why you made that choice there. Save one sine factor to form your du, because if u is equal to cosine x, du is going to be minus sine x dx. So keep one of your sine x to go with your dx and make it that. Okay? Convert the remaining sines to cosines. Well, you only had sine squared left. Sine squared is 1 minus cosine. So that was easy to do. So this will be the integral of sine cubed x cosine fourth x dx will be the integral of sine squared x cosine fourth x times that one that you pulled out there, make that sine x dx, and let that be your du ultimately. Okay, so the first thing we're going to do is change that sine squared into 1 minus cosine squared. So everything except for that is going to be in cosines. 1 minus cosine squared times cosine fourth, and this will just be left as a sine x dx. Okay, now we make our u substitution. Well, not yet. They're multiplying through first. Cosine fourth x minus cosine sixth x times sine x dx. Now they make the u substitution. Well, not quite, okay? They're splitting up differently than we did. They split that one up this way, this one up this way. I don't know why they're going through this rigmarole, but it works. It's perfectly legitimate. And this will be minus, because the derivative of, if you let u equal cosine x, du would be minus sine x dx, and that's what you want here. So since you need a minus in here, you put a minus here. To me, it's easier to do it the other way, but as long as you see what they're doing. Same thing here, the minus sign changes that to a plus there. Okay, all works out the same, and this will be, and I swear, why in the world wouldn't they show the u substitution? It just makes it so clear if you had done it. They're using it, but they don't show it to you, okay? And that to me is just, they make it seem like it's magic here. It's not. It's just a simple u substitution. And that would be minus cosine fifth over 5 plus cosine seventh over 7 plus c. I think they skipped way too many steps and left off the most crucial steps of all. Okay, but once you get to doing them, you'll see it works out pretty nicely. Any questions on that? Okay, now they're skipping example 2, surprise, surprise, example 3, surprise, surprise, and jumping down to the bottom of page 534. So let's us do example 2. I think we've got time to do it. So I'm going to go to the whiteboard and we'll do example 2. All right, now why this came back down here, I don't know, but I'm going to move it out of the way. Okay, and I will clear the drawings on the screen. Does anyone need that anymore? Okay, and let's hit example 2. Now example 2, you can go to larsoncalculus.com for an interactive version of this type of an example. Now, boy, did it get more complicated here. The first one was pretty straightforward. This one a little bit more involved. Here is, if I can find my pen, there it is. Okay, here's what we're evaluating. The integral from pi sixth, definite integral this time, to pi thirds, pretty small range there, okay, of cosine to the third power, cosine cubed x, over, and here they seem like they violate what they were just saying to do, the square root of sine x dx. Because earlier they said whole numbers, positive whole number, positive integers, okay, not whole number, positive integers, okay. Here they have a radical, okay. That doesn't seem fair, does it? Okay, but I think we can handle it. Now, don't know what you think to do, but what I think to do is rewrite this. The integral from pi sixths to pi thirds, okay. I'm going to leave this as a cosine of cubed x, and I'm going to write this one as a sine to the minus 1 half. That's the square root is minus 1 half. It's in the denominator, x dx. Okay. Now actually, if you think back on it, they said that the m and n are positive integers. This is not the case, but we're still going to be able to handle it, I think. Okay, because you do have an odd right there. So let's pull out one cosine. This will be the integral from pi 6 to pi thirds of cosine squared x, going to pull out 1, sine to the minus 1/2 x times cosine. That one we pulled out, we're going to move over here with the cosine x dx. Okay? Now, you got the derivative of sine right there. So let's get this in terms of sine, and that will be, I'm going to come over here because I'm probably going to need more room, the integral from pi 6 to pi thirds of, and change that cosine to sines, which would be 1 minus sine squared x, because cosine squared x is 1 minus sine squared x, times sine to the minus 1/2 x. Okay, not an integral, and then this will just be your cosine x dx. Okay, let's distribute these signs together here. This will be the integral from pi 6 to pi thirds. Okay, distribute here, that would be a sine to the minus 1/2 x, and this will be 2 halves times plus minus 1/2, that would be minus, forgot my minus sign, sine to the minus 3/2 x, and then we have cosine x dx. Okay. Now, this is a lot of writing. After a while, you'll probably learn to skip a few steps here, but let's just draw it out in gory detail right now. Pi 6 to pi thirds. Okay. Now, what we're going to do is a u substitution. And I'll probably regret that I put those there. We'll come back and change that in a minute. Okay. Let u equal sine x. Then du is equal to, derivative of sine is cosine x dx. Okay. Now if we did that, and this is where I regret that I wasn't looking ahead here. Find my eraser up here. Okay. It's far easier to change the limits usually. Okay. Okay. I'm sorry. I've got to get something else. My head is about to lose it. Okay. Now, if x, what we're doing is changing our limits. When x is pi 6, sine of pi 6 is, anyone remember? 1/2. When x is pi thirds, the sine of pi thirds is the square root of 3 over 2. So those are our new limits for the u's. Okay, so what do we have here then? We have u to the minus 1/2 minus u to the, that's a plus 3/2. How did y'all let me get away with that? That is a plus 3/2. 3/2. Okay, and then your du is cosine x dx, so that's just du. All right. Now, again, a power rule. Okay. The antiderivative of u to the minus 1/2 is u to the 1/2. You increase this by 1. Minus 1/2 plus 2/2 is 1/2. And then divide by 1/2, which is the same as multiplying by 2. Minus u to the, increase that by 1, 5/2. Divide by 5/2, which is the same as multiplying by 2/5. Okay? And then we evaluate that from 1/2 to square root of 3/2. Okay? Now, it's a little messy here, but doable. The u is the square root of 3/2. Well, the square root of that would be the square root of 6 over the square root of 2. So I think what I'm going to do is start by just bringing out the 2, factor out the 2 there. And this would be the square root of 6 over root 2. Wait. My head's not running well today. Let me think. The square root of 3/2 raised to the 1/2 power. Yeah, I think I did it right. Okay. Minus, I factored out the 2, and this would be 1/5 times this one here. Boy, this is just, it's just messy. Okay. And we're out of time, so let me just cut to the chase here, because this is to, I'm just going to write it the way they do in the book, which is, it's sort of, okay, this 2 here times the square root of 3/2 to the 1/2 power. Okay, that's exactly what we got there. Minus 2/5 times the square root of 3/2 to the 5/2 power. And this is just messy. Okay, then we have a minus 2 times 1/2 to the 1/2 power, and then minus a minus, which is plus 2/5 times 1/2 to the 5/2 power. I'm sorry. Okay. Now, that is a mess. It is a total mess. Okay. So you have 2 times that minus 2/5 times that minus root 2, and this does just turn into root 2 because this is 1 over square root of 2 times 2, so this just becomes the square root of 2. And then this one becomes, and I'm sorry, my writing's so terrible there. And this is messy. They don't show you how they got this, but it is correct. This would be one half to the 5/2 power. That would be 1/2 squared, which is 1/4, times another 1/2. That would be 1 over 8, I think it is, and then times a 2 here, You'll just have to look and fight through this. It works. It's correct. This is the same as the square root of 32 over 80. Okay, I know it's messy, but that's what it is. Sorry, we ran out of time, but it's just arithmetic there. We'll start next time with, on page 534, if I can get my pencil out, example 3, top of the page, and go from there. Any questions on what we've done so far? Sorry, we ran out of time right at the end there, but we'll begin at square root at example 3. Homework exercises here would be any of the odds 3 through 13. This is on page 538. They're all at Calc Chat, 7's at Calc View. Any of the odds 15 to 19, they're all at Calc Chat, and we'll stop there and pick up the rest of those next time. Okay? All right, sorry we ran out of time at the end. Any questions? Okay, I'm going to stop my sharing then if there's no questions. Goodness, I'm out of energy, out of breath, out of everything. So anything else before I shut it down for today? Okay, I'll end the meeting for all of us. Take care. We'll see you on Wednesday. Okay? Take care. Bye-bye.